Welcome to WebRTC Live. In WebRTC Live, we cover the latest technical topics and business use cases for WebRTC and live video. As always, this episode is brought to you by WebRTC.Ventures, leading integrators of WebRTC video into your custom application.
Welcome back to WebRTC Live. I'm your host, Aaron Syme, founder and CEO of WebRTC.Ventures. WebRTC.Ventures is a custom design and development agency focused on building live video applications, and we're here to help you take your application live. You can learn more about us at WebRTC.Ventures. This is our first episode of 2022. We're using some new tooling to kick off the new year. If you're watching this live, then you're seeing it either on our YouTube channel or on Twitch, and you can ask any questions right in the comments. As usual, we will address those questions after each speaker. We also welcome any feedback you have on this new distribution format for WebRTC Live. In today's episode, I'm excited to have another panel of our developers at WebRTC.Ventures. As you know, most episodes of WebRTC Live are with guests from across the live video development industry. But in this occasional series, we'd like to highlight some lessons that our engineers have learned in our client work at WebRTC.Ventures. So I have two members of our team joining us today, Jacob Greenway and Alfred Gonzalez. Thanks for joining me today, guys.
Yeah, happy to be here.
So Alfred is joining us from Barcelona, Spain, and he'll be discussing some aspects of refactoring WebRTC applications to scale better. Scaling is always an important issue for our clients, so I think that's going to be really interesting to hear some of his experiences. He'll be our second speaker in today's episode. First up, we'll have Jacob, who's joining us from Austin, Texas, and he'll share some insights with us about the Offscreen Canvas API. All right, so thanks both of you for being here. Let's go to you first, Jacob. Let's go ahead and switch over here. Let you share your screen. Tell us a little bit about the Offscreen Canvas API.
Okay, and you guys can see my screen's
we can.
progressing on it. Okay, cool.
Yep, you're
great.
All good.
Yeah, so I'll just get into it here. I'm gonna talk about the Offscreen Canvas today, which is an up-and-coming API that's still a little bit experimental, but just now coming into the more standard API for all your famous browsers out there, so Chrome, Firefox, Edge, everything. So yeah, this is a real-time, high-performance off-thread rendering context for the canvas, and I'll get into what I mean by that in a second here. So first, I'll talk about myself a little bit. So I'm a WebRTC engineer here at WebRTC.Ventures for almost a year now. I've really loved working here. A few of my different hobbies around the technology space include open source, home lab, and real-time video and audio. So if you guys are familiar with any of those, feel free to send me a message or something. I'm always ready to talk about different things with open source or home lab or things like that. So now you know a little bit about me. I'll kind of go into what the Offscreen Canvas API actually does. So this allows the developer to basically take all of the heavy lifting from the canvas that's either rendering 3D objects or high resolution frames or things like that, and take it from the main JS thread, which is running alongside all of the DOM manipulation stuff, all of your normal JS stuff, and put it into a separate thread, which really frees up the browser to display the main JavaScript thread very quickly and display the canvas in an asynchronous way. So this allows for a significant performance boost when doing stuff such as media multiplexing or heavy applications like games or 3D rendering. So this is a really big change for any sort of like high availability type canvas work. So canvas frames are transferred to a worker thread, which is basically a separate thread in the browser or JavaScript world, and the bitmap image of the canvas is actually shared as a like a shared memory space between the main thread and the worker thread, so that the main thread can render the canvas or display the canvas, and the worker thread can actually do the heavy lifting there. There's a few different diagrams down here for how the event modeling and how that shared memory space works. But there's a lot of different documentation on the Mozilla Developer Network site. So if you're more interested in the kind of backend part of this, definitely look into that to see all the different ways this is implemented. So this is a fairly early API. So for example, in Firefox, which is the browser that I like to use, it's still a little bit experimental. So you have to enable a flag in Firefox to use it. But according to this bug that's being worked on by the Mozilla team, this is a very soon to be implemented feature in the actual mainline Firefox API. So this is definitely something worth looking into for the next year or so, for if you're doing any sort of heavy lifting with the canvas. But you'll see on Chrome and basically every other browser that implements Chromium in some way has the Offscreen Canvas API already implemented. So I want to go in a little demo to kind of demonstrate the difference between the default canvas and the Offscreen canvas when doing some sort of very heavy lifting rendering. So let me go into the demo here. So I have this in Chrome because obviously from what you saw earlier, my Firefox browser is not up to date with the current Offscreen Canvas APIs, but I'll show this demo here in my Chrome instance, and I'll open this up here. So basically what this is doing is just creating a bunch of different random circles of different color and size on the canvas, and this is actually rendering in a 4,000 pixel by 4,000 pixel screen. So this is a very resolution heavy operation, which means that on the main rendering context on the main JS thread, this is being bottlenecked by whatever else is being taken into consideration when rendering this. And so we're seeing an output of only 20 to 25 FPS from the default canvas, just because everything else that's in that browser main JS thread is kind of clogging up this rendering context. And then in the off-screen canvas, since all of this rendering is done in a separate thread asynchronously, we're actually seeing this it'll render in its own thread very quickly, and then actually we will grab the different bitmap images that are rendered in that separate thread and just display them here in a much faster way. So this is actually giving us almost real-time 50 FPS frame rate, and the main thing too is this is the reason I actually had to open this tab up when I showed this demo is because if I leave it open for too long, it starts to bog my computer down, just because this default canvas is so heavy on the browser that it actually starts to slow things down. So this is if you're doing something as heavy as 4K resolution type media mixing, then this is a very useful tool to have. So let me go ahead and close it again. And I'll kind of go into how you can implement this on the browser side. And it's actually very easy and simple to set up. So there's a few different ways to set up off-screen canvas. So the one that you saw just now in that demo is this first one, this first bullet point, which is transferring an existing canvas to an off-screen context, which is rendered asynchronously. And you can see kind of a little bit of a code snippet here how this works. So basically you create you get a reference to your canvas in JavaScript, and you use this transfer control to off-screen method that allows you to basically turn that into an off-screen canvas. It creates and then you create a separate worker thread using a off-screen canvas API or file that will actually do all the rendering. So this off-screen canvas.js file has all of your normal draw calls to the canvas, and this is happening in a separate thread because you instantiate it as a worker, and then you actually use this worker.post message to send the specific canvas that you will be drawing to with the calls here. So you'll specify the canvas, and then you'll put in brackets here, which is basically a way of saying what data to transfer the canvas, the off-screen canvas handle. And then the other way is basically where you have two different canvases, and they're both one is drawing, and the second one is actually rendering what the first one draws. So it's a little bit more complicated, and I can go into, let me pull up the, and this is a way to synchronously display the canvas and still have off-screen capabilities. And so this is, if I look at here, you actually have to use this transfer to bitmap image, and it sends the bitmap one by one to the other other canvas, which basically allows you to synchronously display these images on the browser context. So it's a little bit more involved, and they go into a little bit more detail on this on the off-screen canvas MDN documentation. So if you do want to have this displayed with no sort of like input lag, or if you're taking input from a user and then rendering it and then bringing it back, this is probably the best way to do it, so that it's synchronously displayed. So I recommend looking through this documentation to get more details on that. So let me go back into here. So so yeah, the disadvantages to using the off-screen canvas might include, so you have to refactor an existing canvas project, which may be a little bit more involved than you think, just because all of that rendering that has to be done on a separate thread might be mixed around in different files. So that's one thing to take into consideration. Also, the other thing is that the rendering context that this is happening in, the JavaScript file that's actually running as a separate thread, they cannot interact with the DOM. So if you wanted to, for example, you're moving some sort of sphere on the canvas, if that sphere, if it hits the end of the canvas, something on the document changes, that's a little bit more complicated. You have to set up messaging between the worker thread and the main thread. So there's a lot of refactoring there if your existing canvas interacts with the DOM a lot. And then the other thing is it's still experimental, and it's also a little bit more difficult to implement in like React or Angular based projects, just because they use Webpack, and workers are handled a little bit differently than you would think with normal JS files when using Webpack or any sort of transpilation for JavaScript. So just be aware of that. It is possible to use this with React and Angular. It's just a little bit more work to get it set up. So, but I definitely still recommend using the off-screen canvas if you think it's a good fit for your application, just because the benefits heavily outweigh the disadvantages. So yeah, that's it. Hopefully you guys enjoyed that presentation. If you have any questions, feel free to ask me. So yeah.
Awesome. Thank you so much, Jacob. So
yeah,
really cool possibilities there, and the fact that you can like nearly double the performance is quite impressive, definitely. For those of you watching us live, by the way, if you have any questions for Jacob, you can go ahead and put them in directly in the comments to the YouTube live stream or the Twitch live stream, and we'll answer those here either now or at the end of the episode. So feel free to put in those comments. I'm curious, what specific types of use cases would you imagine this being useful for, Jacob?
Yeah, so one of the biggest use cases that I found in one of the projects I worked on a while ago, just like an open source project, was when you're taking multiple screen shares and cameras and all these different video inputs, and you want to combine them into a canvas in some way, like kind of like we're doing now with the live stream. That can take a heavy toll whenever you start to get up to high resolutions. So if you have like two different 1080p streams, merging them on a canvas can be very cost intensive. So having that rendering in an off-screen context is very, very helpful.
Nice. Okay. Very cool. And you mentioned it. We'll make sure that I understood this correctly. So this works now. You can use this in Chrome, not just in Canary, but in regular release Chrome version. Is
Yes.
that correct?
Yeah, the Chrome that I was using then is just a mainline, whatever the latest version is. So
Okay. And Firefox, that's not the case yet. Did you mention Safari? What's the support in
let
Safari
me
at this point?
pull it up really quick because yes, that should be, I think, in Safari. And Safari is notoriously terrible at picking things
Always
up.
lagging a little bit
Yeah.
behind.
Let me pull up that slide I had. Yes, Safari does not have it right now, and neither does Internet Explorer, but that's to be expected as well.
Right. Internet Explorer doesn't have anything,
Yeah.
but Edge, I imagine, would, because it's based
Yes,
on
it's
the
all
Chrome
Chromium.
engine. Yeah,
Right.
exactly. Okay,
Right.
cool. Excellent. Great. All right, excellent. Alfred, any questions for Jacob?
I don't have any questions.
All
It
right.
looks cool. Yeah.
Yeah, it does look really cool. Look forward to seeing more
And
of this.
useful.
Yeah, definitely. There a good amount of extra work, it sounds like, to implement this, especially in React or Angular. So that's, word of warning, I suppose, as well as a bit of timeline before you could use this in production, unless you're able to restrict your users to using Chrome or Chromium browsers. But still, some really, anytime you can nearly double performance of rendering, and especially with more 4K media out there, I think this sounds like a really, really useful API to get to know. And I'm sure over the next year, we'll be seeing people using it more and more. So thank you very much, Jacob, for that presentation. I appreciate it.
Yeah, of course. Yeah.
All right. So next we'll be going to Alfred to talk to us a little bit about scaling WebRTC applications. But first, before we do that, we're launching a training program in WebRTC at WebRTC.Ventures, and I want to tell you a little bit about that first. As a viewer of WebRTC Live, you already know how important WebRTC development is to the modern web. Now it's time for you to grow your career by learning to build live video applications and joining our team at WebRTC.Ventures. Go to WebRTC.Ventures and apply to join the next cohort of our WebRTC training program. You'll have free access to advanced courses, mentorship from our team, and those who are accepted into the second month will receive a paid development contract and join our team of WebRTC development experts. Go to WebRTC.Ventures now and earn your place in our team of video development experts. All right. So please do check out that training program that we have at WebRTC.Ventures. I think this is a really fascinating field to be working in right now. And if you want a chance to work with Alfred, work with Jacob on a project, I know you'd enjoy it with anybody in our team, and a lot of great, cool clients. So do check that out. All right, next, let's bring Alfred on to the stage to talk to us about refactoring a WebRTC app for scaling. So Alfred, take it away.
All right, thank you. So I'm Alfred Gonzalez, a WebRTC engineer at WebRTC.Ventures, and I'm going to talk about refactoring a WebRTC app to scale. So increasing the amount of user connections a WebRTC app can handle is an important part of our work. If we set an infrastructure that is able to scale, then we can provide the resources as needed. In our case, we upgraded our infrastructure by setting a Kubernetes cluster where multiple instances of our services could run. This way, if there is an increase of users, we can increment the number of instances of the services we are running in the cluster. And if there is a decrease, we could also free some resources. And this way, we are able to handle the demand we are facing. And another benefit of this infrastructure upgrade is that in case of a service failure, we will have other instances of that service running. But this type of infrastructure upgrades comes with some issues we have to face. And I'm going to talk about some of the issues and how we manage to solve them. The main problems are related to communication and data management. In our application, there are two main services, which are the REST API and the wrapper. The REST API receives requests from the client and sends messages to the wrapper. And the wrapper handles all the current-related logic. So we have to be able to make requests from service to service, which we were already doing before the infrastructure upgrade. But now we have multiple instances of a service. And we want the request to be only processed by a single instance of a service. So for example, we wouldn't want to create the same connection twice in two different instances of the wrapper. And we were using RabbitMQ for the communication, which already allows us to consume messages only once, even if there are multiple consumers of the same queue. So for example, the client are sending messages to the REST APIs, and those messages are being sent to the session queue, and the messages would be consumed by the wrapper's listeners, and not a single message would be consumed twice. And later I will explain how we set up those session listeners for the wrappers. Also, we have fan-out exchange, where we can send messages to multiple queues. So we can send a single message to multiple users of a session. For example, we have a session with 2 users, and there's a third user that joins. That user would send a request, and the request would arrive to a wrapper, and the wrapper would send a single message to the session exchange that a new user arrived. And that message would arrive to all the users that are bound to that exchange. So we send the message to the session exchange. We have 2 user queues bound to that exchange, and the message would be consumed by both queues. And we can also send messages directly to the user queue, and all the messages would be stored in the user queue until they are consumed. And we use HTTP polling to receive all the messages sent to a user. That is that a user is sending a message to the REST API to receive all the messages sent to its queue. And it would consume all the messages that were sent directly to the queue, which for this example would be the message 2. And all the messages sent to the session exchange, which would be the message 1. And this way, we have all the messages being received by the users. And the same would be for the user 2. He would send a HTTP poll and would consume the message 1 and 3. Why do we need data persistence? So previously we had data stored in the service memory, which makes it vulnerable to server failure. We wouldn't be able to retrieve the data if the server dropped. And furthermore, since each instance of a service, for the wrapper, for example, can process different requests of a session, the instances would have different data. There would be data inconsistency. So we could have the session 1 with 3 users connected, and the wrapper 1 would have 2 users and the wrapper 2 only 1, and we wouldn't be able to create the connections between user 1 and 2 and user 3 and 2. So we decided to use Mongo database to store all the data related to a session, which are the users, their connections, and some other data. This way, we are able to process requests from all instances, and the data will be consistent. since we will be reading it from and writing on the Mongo database. When we create a session, a message is sent to the REST API from the client, and it will create a session queue, which would be the queue session 1, and it will send a create session message to the wrapper queue. But this message will only be consumed by a single wrapper, which in this case would be wrapper 1. And wrapper 1 would create a session message listener for future requests on the queue session. And it will also create the session, insert a new session in the database. This session message listener is the one that handles all the requests, like the joins, the offers, the ICE candidates that will be sent from the clients. And besides storing the data from that session, like media pipelines, new users, and connections, it will also create the WebRTC endpoints, connect the endpoints, gather ICE candidates, send answers, send ICE candidates. We'll do everything we need. But this way, only a single instance of the wrapper would process the requests to a queue. We only have this listener set right now. And we want all other wrapper instances to be able to process requests that go to that session queue. So to do that, we used reactive streams from MongoDB, which allows us to set listeners to data changes in the database. In our case, we set a listener for inserts in the session collection. So when the create session message goes to the wrapper queue and is consumed by the wrapper 1, it will create the session message listener and also insert the new session. And this would trigger the reactive stream, which is set for all the wrapper instances. So if we had two more wrappers here, it would trigger for all the wrappers, and that would create the session message listener for that wrapper. So we could have all wrappers consuming from the session queue. This allows us to process the requests with multiple wrappers. So future requests to that session queue would go through any of the consumers, through the message listeners we set. We also had an issue with storing the data, since there are some objects of our session object that can be stored directly into Mongo database. For example, the media pipeline and WebRTC endpoint can be stored in MongoDB. So to solve that, we used custom conversions from Mongo for reading and writing. It maps MongoDB documents into our Java objects and vice versa. So for example, we could have a session with a media pipeline, and when we store it in the database, we would store, instead of the object, we would store the media pipeline ID. And then when we read the session back, we use that ID to retrieve the media pipeline object using some Curento client methods. So we would get the Curento server of that session, then the pipelines of that Curento server, and then find the pipeline that matches our ID. This way, we would retrieve the media pipeline object. And we also faced an issue with data consistency when multiple wrapper instances were modifying the same session at the same time, or a similar same time. So imagine from session 1, we have two users, user 1 and 2, each one with 2 connections. And then there's a a new user, the user 3 that is joining, and it's sending requests to the wrapper. And the wrapper, the instance 1 of the wrapper, so wrapper 1 would receive a request to add connection 3.1 and wrapper 2 to add the connection 3.2. And wrapper 1 would, so both wrappers would read the session object from the database, which would be with 4 connections. They would read it at the same time or similar time. And wrapper 1 would add that connection, the connection 3.1, and store it. But later, the wrapper 2 would add connection 3.2 to the same object and store it, which would override the data that was changed in wrapper 1. So we would lose some data there. The solution was to use partial updates. That is to modify the data that is required to be modified instead of the whole document. So instead of getting the document, modifying it, and storing it, we are filtering and updating at the same time. We use the update one method from Mongo collection, which accepts a filter that matches the document you want to update and an update statement. In the update statement, you can specify the changes that need to be applied using update operators. We used set, push, and pull, and also the array identifier. This way we can set a specific value, push a value into an array, or pull one element from an array. So, for example, we had the whole session with 3 users and all 3 connections. If we want to remove the user 3, we can delete that user from the Mongo database by pulling the user 3 from the user array of the session, where session ID equals 1. And this way we would remove this user and all the connections. And we can also delete the connections linked to that user, which would be connection 3.1 and connection 3.2, from all users of the session 1 by pulling all the connections with a user value 3. And another thing worth to mention is how to handle the reconnection. We have 2 different cases, which would be when a KMS drops when a KMS drops or a client drops from a call. So if a KMS Currento Media server goes down, we would need to connect all the users that were in that session using a different KMS. And in the second case, with the client dropping, it would only require a user to reconnect back to the session. So when a KMS goes down, all users, all the clients, would get a disconnected event in the browser, and they would try to send a reconnect or join message to the REST API and then to the wrapper. And when handling the reconnect request of the session, we detect that there is no media pipeline since the server is down. So the media pipeline of the session doesn't exist. Then we check for KMS availability. We may have multiple KMS for the cluster. And when checking for the availability, we try to reconnect the KMS that has dropped, and we select it if it's working back again, or we can select a different available KMS. That would be the one with the lowest memory usage. So we look first for availability, try to reconnect the ones that are not available. And the ones that are available, we select the one with the lowest memory usage. Then we just create a new media pipeline for the session reconnection and save it in the Mongo database. And all future requests that go to that session will use the new media pipeline to create the connections. And if a client drops, it will try to reconnect to the session, sending join requests to the REST API. But it can sometimes be too sensitive. We've seen micro drops, and we don't want the client to try to reconnect when there's a micro drop that doesn't even disconnect the user. So we need to limit the reconnect sensitivity. We could add a timer or a counter before trying to reconnect. And that would be it. If you have any questions.
All right. Thank you, Alfred. Really interesting topic there. And for those of you watching live, if you have any questions, now is the time to put those into the comments in YouTube or on Twitch. Alfred, the last part that you talked about there is really interesting, and you used the term micro drop. So I want to ask you to give a definition of how do you know something is a micro drop?
Yeah, that's an issue we were working on. Like, we implemented the reconnection, and we saw that there were some cases that a user was detecting a disconnected, like was receiving a disconnected event, but it had connection.
Mm-hmm.
And that's the reason that we want to implement this this way, a timer or a counter to see, like, instead of sending the reconnect message when we receive the first disconnected, we, for example, can wait for to see if there's a reconnect event sent in the received by the client, or we could add a counter to wait for a reconnect in the client before sending requests to the application and restarting all the connection for that user.
Nice. Yeah, so it's interesting. I mean, with a lot of these things, kind of like when you're looking at memory usage on the Corrento media server to decide if you can use it or not, essentially you're setting a threshold for a lot of these things, right? And so in that sense, when a lot of the things that the team you've been working with has gone through in terms of scaling this particular WebRTC application are similar to what you would do in scaling any type of web application, right? You're going to look at things like memory usage and look at certain thresholds of what is acceptable for your application, that server is still going to do a good job of rendering the application or delivering the video, handling the media, whatever you're doing, right? So in some sense, these are standard, that doesn't mean they're easy, but typical scaling considerations that you would make. And then in other cases, they're specific to WebRTC and video messaging too, because I think when you talk about the importance of RabbitMQ and stuff in this architecture, it's really all about delivering those messages reliably to the clients, even if a media server goes down, correct?
Yeah, that's correct.
So in the RabbitMQ, are all of the messages that you're using that for, are they basically around the WebRTC connection status, or is it used also for like text chat or other things in the application?
No, it's for the signaling. We use
for the signaling, yeah.
Yeah.
And I think an interesting thing about this, and obviously we don't want to say anything about giving away the identity of this particular client. We always respect the privacy of our clients and confidentiality. But one of the interesting things about working with this client is that two of the big, as I recall, correct me if I'm wrong, Alfred, two of the big constraints that they had when we started working with them was they had a legacy system based on Corrento Media Server. And so we needed to decide if that legacy system could be used, if it could be scaled, if we should continue to use it or build from scratch. That's always a really hard thing for any software development team to work through, of deciding when do you start over, when do you refactor and improve an existing application. And in this case, we went with refactoring an existing application, but that led into a lot of these other considerations and concerns that you've described too, of having to refactor how messages are handled so that it can scale better, for example. And then the other big constraint that in this particular project was that they need to be able to host internally the application, right? So we were using a pretty much entirely open source stack, right? As I recall, right? So so that helps drive the choice of RabbitMQ, I presume, for the queuing technology. If they were using commercial services, that's something that we could have also looked at. If you didn't want to deal with some of the infrastructure around that, we could have looked at things like PubNub or Subspace or different commercial real-time messaging solutions as well, correct?
Yeah, that's correct.
Yeah. Yeah, interesting. Jacob, any questions on your part?
Yeah, yeah, I actually had, so I noticed you mentioned Kubernetes at the beginning. Is Corrento put into a container, and then like, is it auto scaled in any way, or I was just curious how that specifically worked.
So yeah, we had a specific number of containers for each service. So for example, we could have 2 instances for each service, like for a Corrento media server, for the wrapper and the REST API and other services that we have in the application.
Okay, got it. Thanks.
All right. Well, thank you so much, Alfred. Really appreciate it. Thank you, everyone who is joining us today for WebRTC Live. As always, we will post this video to our YouTube channel as well as to our blog at WebRTC.ventures. Our next episode will be Wednesday, February 9th, and we will be talking with Lorenzo Miniero, an old friend of the WebRTC Live program, as well as ours at WebRTC Ventures, and well known to many of you in the WebRTC industry as the co-founder and chairman of MeetEcho and author of the Janus WebRTC server. So make sure you join us for that on February 9th. And to find out more about our upcoming episodes, follow us on Twitter at WebRTC Ventures, on Twitch, on YouTube, and join our email list at WebRTC.ventures. So thank you, everyone, for joining us today. Let's make it live.
Thanks for joining us for WebRTC Live. Visit our website at WebRTC.ventures to learn more about our custom design and development services, and to learn more about upcoming episodes of WebRTC Live.